So it's a pleasure to introduce Claude Bardos, that is going to talk about boundary effects and turbulence.
Really enjoyed the atmosphere of this meeting. It's not on. Okay. Enjoyed the atmosphere of this conference. It's extremely pleasant. Learned a lot. Reminds me also of the time when Henri Cartan and Adrien Douady tried to teach me mathematics with a limited success. But in fact, I think it's Adrien who introduced me to Dennis or vice versa. So to conclude, I'm very happy to be here. So here is the title. And to illustrate this title, in fact, I will consider three equations, which are on the next slide, which are known, I guess. Up. Here they are. I will consider three equations. One is the Euler equation, which has been written more a lot. And here is the Navier-Stokes. And behind that, I will also use the Boltzmann. Now, what? What is Boltzmann? Yeah, get rid of the hand. Okay, thank you. Nothing to do. And mainly, I'm considering this limit. And I want to consider that in the presence of an obstacle, or the typical obstacle will be a wing, or inside a box. So either omega is here, or omega is there. And the point is, I want to try to understand this limit, and there are omega is the domain of the fluid. And I use, as you see here, I will use, that works, that doesn't work? Yeah, that works. I will use Lagrange Eulerian coordinate, which means that u of x and t is the velocity of the particle which at time t sit at the point x. So, and this equation have been written by several, at least the first two, not the last one, because I want to say, before going on, that this problem is mostly in the most interesting part, it's a problem which is open. And there are some partial results, very few. The one that I find the most convincing is the result which is due to Toshio Kato. And what I like in this result is that for me, it appears to be the most natural way to make the connection between deterministic mathematics with convergence, Sobolev spaces, whatsoever, and the notion which appears in the statistical theory of turbulence. So that's the reason I wanted to do that. And since the explanations are not very clear, the only thing I was also able to do is to look at this arrow and to prove that the situation, the problem, the conjecture, the things which are solved, the things which are unsolved, are exactly the same at this level. So that's a parallel between, and in some sense, that will give some foundation of this theorem of Kato, which I slightly improved, and on which I want to talk. So I am almost finished my talk this way. Okay, nevertheless, I go on details. And if I go back to the Navier-Stokes equation, I want just to recall that there are 4 basic numbers which are used in practice. First is the Reynolds number, which will be defined on the next pages. There is the Knudsen number, which in some sense measures the density of the fluid. There is the Struccial number, which measures the scale of the time. And most important is the Mach number, which measures the ratio between the velocity, consider the velocity of the fluid as a perturbation of a reference velocity, which will be the sound speed, and measure the ratio of this velocity with respect to the sound speed. Now, I want to say that because we have heard about Euler equation related to measure preserving diffeomorphism to the world of incompressibility, it's important for practice and for understanding this issue to keep in mind that the Euler equation, the one that you would call incompressible, is in fact a tool to describe compressible fluid when you are not far from when the Mach number is small. You make an expansion near small Mach number, and you find out that the Euler equation is the Navier-Stokes, which you will call incompressible, is a good tool to describe computation or qualitative property in this regime. For instance, a rather better name than incompressible will be divergence-free, and divergence-free will be solenoidal. And if you look back to the original paper of Leray on Navier-Stokes, I think he never uses the term incompressible. It's a solenoidal fluid, and
Excuse me, Claude, could you repeat the statement that something is an approximation to something else? I didn't understand.
I understand. Take a reference velocity, u bar, and look at a problem where your fluid is 1 plus epsilon g epsilon that multiply u bar. And look, or let's do u epsilon. And look and assume that this epsilon describes the ratio between the reference velocity and the Mach number in some sense. And look at an equation for this quantity. Plug it in the compressible 3D Navier-Stokes equation. And let epsilon go to 0. Look at the first order approximation. You end up with the incompressible equation, with the equation you call the incompressible. Okay? Incompressible Navier-Stokes. And why incompressible Navier-Stokes? Because that will come on the next slide. Because now, among this number, of course, so I should keep right, even if it has been written old during previous lecture, I should write dt of u nu plus u nu nabla of u nu minus nu time the Laplacian of u nu plus the grade of p nu equals 0 and divergence of u nu equals 0. That has been written, and you know that with nu equals 0, this is the Euler equation. Now, in practice, if you look at what's happened in the air, the air around a bicycle is the same as the air around a bird or the air around a plane that takes off. It has its own velocity. What has a meaning when you analyze the problem is the rescaled problem where you compare the velocity to the characteristic length, the characteristic time, and then what happened is that you replace this number, nu, by a number which is 1 over Re, where Re is the initial of Reynolds. And in all the application that you have in mind, that I've wrote it, this Reynolds number is very large. For a bicycle, it's 10. For the fluid in a pipe or ship, it's 10 at the power of 4. Around an airplane, it's 10 at the power of 6, and so on. So it's natural at the level of engineering, at the level of computation, to look at what happens when this nu go to 0. That's a good natural assignment. And then, of course, for nu equals 0, you get the Euler. Now, going to the Euler, there are things which are natural and others that are less natural. So that will be on the next slide. The first thing is that if you have no boundary, forget about the object of my talk, then there is a good belief that the Euler equation will describe the limit of the Navier-Stokes. And in particular, assume you want to solve the Clay price, it's clear by now that any answer lies in the Euler equation, not in the Navier-Stokes. And I want to just to give you some comment for that. People have studied like mad this equation using the scaling invariance, using the ellipticity, trying to see in which spaces it is well posed or not. I can make a kind of fake Euler Navier-Stokes, this first one, let's say, plus, I will write it explicitly, sigma over I equal 1 up to n, du nu over dxi equals 0. That's 1. Then there's a second du and the minus Laplacian of u, excuse me, minus nu time the Laplacian of u nu equals 0. There is the second one which I write. It's minus nu time the Laplacian of u nu. And then I put something which has the same dimension, the same scaling, which will be minus the Laplacian at the power 1/2 applied to u nu square. And I take this one scalar. These two equations have the same scaling, the same intrinsic property, except they do not conserve the energy. Then I leave you as an homework to check that there is one which has blown up in a finite time and the other one which has global existence. And there are many other examples of this family. So the message from that is that you have no hope from the Navier-Stokes. It's from the Euler equation that you may have some progress on the understanding. Okay, so that's one thing. Now, it's clear then, the other good news, which has been mentioned already here, is that in C1 alpha, the problem is well posed for the Euler equation. That goes back to Liechtenstein. It was the talk of Sasha. There is another remark which I can make, is that instability for the Euler, that it has been really reasonably well understood in the recent time, and there are thousands of examples now. I want to leave also as an homework a very simple example. I take x1, x2, x3. I will consider the flow in a slab like that, Euler equation, or let's say I will consider the Euler equation. I have u, and I'll consider a flow which is the following one. u1 depends only on x2, u2 is 0, u3 depends on x1 minus t time u1 of x2, and 0 and x3. Okay? So I leave you as an exercise, on x2, excuse me. Here. So it's x2 and 0. So I leave as an exercise to check that this is an exact solution. It's divergent free. It's an exact solution of the Euler equation. And you can see that it will preserve the energy, that you will have solution. If in the initial data is in C1 alpha, in agreement with the theorem of Vol-Ibner, it remains in C1 alpha. You can check that. And if it is in C0 alpha, immediately it loses regularity and jump for T positive just in a space which is less regular, which is C0 alpha square is smaller than alpha. So that's the simplest example of an unstable problem. Now there are many others, Sasha will talk about that tomorrow. There are many other examples for the Euler equation where the problem is badly posed. Now I move, That's what I said. There are many examples, in particular after Sasha and Schaeffer. People have construct solutions with local energy, starting from zero, going to zero, that are weak solutions that will solve the energy crisis, because they start from nothing, they go to nothing. And, in fact, it's interesting just to see that in our present knowledge, the construction has much to do with the invariant embedding. But that's not really the object of my talk. Now, moving on the Euler equation, one thing which has not yet been discussed here is that there is a magic number, and this magic number is 1/3, which is here. Okay, why 1/3? Because you would like to associate you would like to relate the regularity of the solution to the conservation of energy. If you write dt of u, that's what already this morning Steve talked, ui du over dxi plus grad p equals 0, you multiply by u and you integrate by part, you get formally dt of u square dx equals 0, which is the conservation of energy. Now, if you want weak solution, to give a meaning to a weak solution, you replace that by the sum of d over dxi of ui, d of dxj, ui, uj, which in fact is the trace of the matrix gradient u tens O time u. Okay, and then this has a sense, even these two guys are in L2. But now you have a problem, which is, can you prove the conservation of energy? Because then if you multiply, take the scalar product of this thing here with u, the computation may not be valid. It can be valid if you can approximate by smooth solution. Now, to get the approximation, it's quite simple. You look at this quantity, it's a cubic, you distribute the derivative over 1 over each term, so you end up that this term will be, and it will be true for approximation, like a derivative of the order 1/3 applied to the function u, and you take it in L3. So that's an observation which I learned from Shidkoy. And in fact, it's formal, but it has been made rigorous by several people, Constantine A. Titi, or other people who have shown that below this weak solution that will be more regular than 1/3 in some good space that will make that rigorous, conserve the energy, less rigorous, they cannot say anything. And at present, I think that Telelis and Seshkedelidi do have construct solutions which are less regular than 1/3 and that dissipate energy. So you have a notion of critical index that will come later on. Okay, so now that was for the mathematics. Now for the physics, it's clear that the Euler equation is of no use. It's of no use because we have already said that weak solution can be anything. Second, there is this very nice observation of D'Alembert, who picked up the Euler equation and proved, and it's in 3D, that if you describe the flight of a bird, he had no plane by that time, then the bird cannot fly, or at least they cannot glide. And the reason is very simple. You compute the force by integrating on the boundary. You compute the fact that it goes at rest at infinity, and you find out the total force is 0. This is a computation which is not valid in 2D. In 2D, because the kernel of the inverse of the Laplacian is just a log, the decay at infinity is not so good. And as a consequence, one can find that in 2D, there is some force. So in some approximation, people use that. It's called the Kuta-Joukowski condition. But to really use it, you will need to have a plane that has a wing which is 2D, which means it's infinite, which is not the case. Okay, so that's the story. That's the guy which are in this problem. And the clue to make the bird fly is the effect of the boundary, on the boundary. Now, what, as I announced, I want to compare this issue with the turbulence. Now, there are two things that are natural to compare. I will erase that. Two natural things to compare. Which side is? Oh, it's this one. Okay? So, your Euler equation in Euler coordinate, it's, you have the term ui, uj. If I start from Navier-Stokes, but uij, uj, nu. The problem is that the only estimate I have is an estimate in L2. And if I look, I will get very easily that uij converge weakly to ui when you modulo extraction of a subsequence. Now, the issue is that if you take the product, u nu I, nu j, ui, uj, nu, you take the tensor product, then if you just have weak convergence due to oscillation, in general, this thing will not be equal to the tensor product of the limit. And that's a standard thing in nonlinear analysis. And if you are not convinced, look at the limit of the distribution sinus nx, which goes weakly to 0, and sinus nx square, which goes weakly to 1/2. That's an example. OK, that's the main thing. And as in the exam construct by Sasha and Schaeffer, it's related to oscillation. Now, you measure that, as I've written that on the board, and you see that you take the difference between this quantity and this one, and this is known in engineering science. It is called the Reynolds stress tensor. OK? Now, there is a very simple thing to observe, is that this tensor is positive, ui minus its limit, tensor ui minus its limit, and it's this quantity is equal to the limit of u nu tensor u nu minus u bar nu tensor u bar nu. That is the defect of in the weak convergence. Now, that's for weak convergence. Now, people have built, since what you observe is extremely complex, they have the idea to describe fluid not by weak limit, but by an average of a random variable. And though they never say very precisely, this is an open problem, what is exactly the meaning of this average. But say, assume you have some type of average. And if you have some type of average, you end up immediately with the fact that the average of the tensor product in general will be different than the tensor product of the average. And what is and when you make a theory like that, it's essentially credited to Kolmogorov. If Kolmogorov finds out a magic number, here it's 2/3 because it's square, but it's the 1/3 of a few minutes ago, which says that the turbulence, that will be a definition of the turbulence, will be that the average of the fluctuation u of x plus r minus u of x squared at the power 1/2 is equivalent to nu time the average of the dissipation of energy to at the power 2/3 that multiply r at the power 1/3. This number is just an effect of scaling. But the important thing for my talk is that in this regime, this number, nu, the average of nu square, does not go to 0 when nu goes to 0, but goes to a finite quantity. And in the meantime, if I look at the corresponding, let's say, deterministic solution in the sense of weak solution, I replace the average by the integral. You see nu goes to 0, but if the solution u nu oscillate, then the integral over omega of gradient of nu square does not go to 0, so the product, which is bounded, you will see, may go to a finite quantity. So the issue of turbulence will be whether this quantity goes to 0 or not in the deterministic case, and if it doesn't go to 0, we are in some sense a turbulent regime. And this is what is well illustrated by the Kato theorem. And at the claim of the rest of my talk, I want to say that in the presence of boundary is the situation where one sees the most clearly the relation between the dissipation of energy and the appearance or non-appearance of turbulence. Okay? So once again, I look at the problem of the convergence of Navier-Stokes to Euler to start with, let's say near my favorite wing. Assume, of course, that there is no air which goes inside, which means that like in Euler, u nu dot n normal is equal to 0, the normal component is equal to 0, and I want to introduce some boundary condition and see how discuss the effect of the boundary condition related to the issue that the integral from 0 t nu times the integral of gradient of nu square dx dt goes or does not go to 0. That's the game I want to play. Okay? Now, and to consolidate that and to prove that the boundary conditions which are introduced are valid, have some reasonable meaning, I will introduce a series of different types of boundary conditions. First, I want to recall that Kato did the thing when u nu is equal to 0 on the boundary. This is called the no-slip boundary condition. And in 2D, people know that we have heard this morning that everything was solved, and the other day in the Euler equation, it's known that the Euler equation has a smooth solution. It's known that the Navier-Stokes equation has a smooth solution. There is no theorem, absolutely no general theorem that will tell you whether the solution of u nu, the Navier-Stokes, converges to the solution of the Euler. This, even if you solve in 2 or 3D the problem that gives you the Clay prize, this will be still open. And even if you consider the problem on a sphere or a circle, which is completely explicit, with a fluid which has a constant velocity, what's happened behind the fluid, describe it mathematically, is completely open. Nothing. So, just to explore, to see how far I can go, I will measure how the boundary affect the fluid. I will introduce a number lambda of nu. Lambda of nu, it says in how much the boundary is sticking on, the fluid is sticking on the boundary. So that will be the friction hypothesis. And I will look at all type, because I will need that for the rest of the talk, all type of boundary conditions which should have form nu, the normal derivative of nu, plus anything which act on the tangent derivative, plus this friction coefficient equal to 0 on the boundary. And observe that if I take Dirichlet with a lambda, if I take lambda equal infinite, it's the Dirichlet. It's a bad case. Now, if I introduce the different type of boundary condition, the one which introduced the stress tensor, the one which introduced the vorticity, production of vorticity on the boundary, I just observe that since the velocity is tangent here, normal to the boundary, all these boundary conditions can be written on the form which is above. Okay, so that's a simple computation. So then I use the fact that if the function is in H1, it has a trace on the boundary. So with the weight nu, it has a trace. So mu, so square root of nu, the norm of the gradient of u in L2 is bounded. So you turn the crank, you multiply by u nu, and you end up with this energy balance, which is written in black, with a right-hand side, but the right-hand side can be balanced by the left-hand side, so therefore it's bounded. So at the end of the day, for all kinds of boundary conditions, you see that for Navier-Stokes, you have u nu of x and t, which whatever the boundary condition here is less than exponential c nu t, the integral of omega, or the integral of the initial data. Plug that in the equation above, you have this balance of energy, which is the variation of kinetic energy, the dissipation of energy, and the friction energy. All that goes to zero when you go, as a right-hand side, which goes to zero when u goes to zero. So that's very simple. So then, the first thing, as I said this, I already mentioned this question of weak convergence, take the difference, and the point which is written here is the counterpart of what I said. Now, you assume that u nu converge to a weak solution. You assume that u nu converge weakly, that's always true, modulo subsequent, to a solution of Euler. And now you assume that this solution of Euler is smooth. You know that exists, at least in 2D. Then, just by the fact that the weak limit here will be less than the limit, because the norm is semi-continuous, and it is less than the norm of the initial data, since it is a smooth solution of the Euler equation, you have equality on both sides, and you have that the sum of the kinetic energy and the friction energy goes to zero. So, you know, if the solution, if the limit is a smooth solution, which means something like that, then you are okay. That means that there is no dissipation of energy. That's an easy part, but an important observation. Okay, now I move and I want to explore maybe what's happened in a more general case. We have to characterize the limit and make a difference between the notion of limit and the existence of a smooth solution. There is a reasonable notion which has been introduced, which is called the notion of dissipative solution, which I may use. In fact, it's an idea which goes back to Dafermos for hyperbolic system, where there were shock and use entropy, and one can use it for the Euler equation. Since I will use it, I will call it in two lines. That's not a big deal. I want to construct some criteria to decide whether a limit is solution of the Euler equation or not. Okay? Now, to do that, what I do, I have a solution of the Euler. I take a smooth vector field tangent to the boundary and divergence free. So it is not solution of the Euler. But I take the difference, I take u minus w, I multiply by u minus w, integrate, use the standard integration part by part trick of the theory, and end up with an inequality which is of the type of the Grunwald lemma. And then the state definition is that u will be a dissipative solution if for any smooth solution w, any function w, such inequality is satisfied. Immediately you see that if E is equal to 0, then you will have a real Grunwald lemma because this tensor is smooth, and with a real Grunwald lemma, you will have a stability theorem. In some sense, that says that you have stability between strong solution and dissipative solution. You have a strong solution, you have a dissipative solution, then you have stability. That's very good. But then the problem is that to prove that at the limit, starting from Navier-Stokes, you get this relation, turns out to be perfect when there is no boundary. When there is a boundary, the same problem appears. Because if I want to use that to test again a solution of Euler, then I need to include in this business vector field which do have a tangent component. Okay, and that's needed. Okay, so far so good. And then what's up? I move for one, and I look at what happened with boundary. So I have this quantity. I've already said that if you have conversion to a smooth solution, this quantity goes to 0. In general, I have a very simple estimate, which is that the square root of nu, integration from 0 to t, the integration of the friction is, this quantity is bounded. This is just Cauchy-Schwarz. But then that says that if I want to test, if the limit is a smooth solution, if the limit is a dissipative solution, I will just have one thing to check, is whether or not the integral on 0 to t or the integral on omega of du d nu n dot w multiplied by nu d sigma d t goes or does not go to 0. And because to test whether you have a dissipative solution, you multiply the equation, then you multiply the Navier-Stokes by a function w, you integrate by part, and you see that the only bad term will be this one. All the rest are nicely controlled. So all the issue comes from the production of vorticity at the boundary. Okay, so far so good. So I am in a situation where if this quantity goes to 0, okay, it's the Euler equation. If the coefficient, if lambda nu, u nu goes to 0, since this is the same thing as with my boundary conditions, this is the same thing as this boundary condition. If this goes to 0, then that goes to 0, then the normal derivative of u nu goes to 0. That's easy. So the point, so that gives the second easy result, which is that if lambda u nu goes to 0, then I have also convergence. Now, if lambda nu, just lambda nu goes to 0, or if lambda of nu is bounded, and if the energy of friction goes to 0, then I have also the same result. Now, if none of these two hypotheses are satisfied, I am back in the case where the problem is open. And that's the case where one can generalize the result of Kato in the way that I will say. And generalize the result of Kato in the following sense. I look at the favorite wing, and the result of Kato is the following. You have one alternative. Either u nu converge weakly to u bar, and then the energy goes to 0. Goes to 0. The dissipation, energy dissipation goes to 0. That's one case. That's, let's say, and conversely, if the energy dissipation goes to 0 in a very small layer, Small layer will be a layer of the size of nu, is here, distance of x over d omega less than nu. That implies the same thing, the convergence to a solution. Now, for people which are used to boundary layer analysis, it's a starting, it's something which has to be noticed, because usually people that do boundary layer analysis analyze the boundary layer in a region of the size of the square root of nu. And this, what was done by Prand, who was the person who analyzed this thing, but you observe that if you have a boundary layer in the size of square root of nu, then in a smaller size it will go to 0, and in particular in the size of nu it goes to 0. So saying that the boundary, that the vorticity in this region, because they're the same, goes to 0, is the criteria not for the boundary layer, but from the fact that nothing will appear later on. Okay? Now, I'll maybe skip the proof of Kato. What I want to say on the proof of Kato, it has two legs. One leg is to construct a good test function that will lead to the dissipative solution, and the other leg is to test this test function against the solution, which is here. You take the solution, you multiply by W nu, and you end up by the fact that the only quantity that you have to estimate is this quantity. Since the test function lives in a region of the size nu, that will be, this gradient will be of the size 1 over nu. For the other term, you will use Poincaré estimate and show that it goes to 0. Now, this is the picture to illustrate this thing. This really the only theorem which I know which really relate the fact that away from the boundary here, it will be turbulent, with the fact that this quantity, gradient of u nu squared the x dt, goes or doesn't go to 0 even in the boundary of size nu. And really, that's the only mathematical theorem which made the connection and which make appear this idea of turbulence with the fact that this doesn't go to 0. So I like this picture for several reasons. The first is that there are several problems standard in fluid mechanics. One is called the boundary layer, which is due to Prand. There is the von Karman vortex street, which is what you see there. And there is the Kelvin-Helmholtz. Now, if you make a search on the web and look for any of these keywords, after a while, you end up with the same picture. Since there is this picture on the board, I just want to make a comment. So you see the plane has created some condensation of vapor, which means that you have two phases in the back. And here you have two phases which are related by a very bad, looks very wild interface. Now, this problem, when the two phases are almost the same, because the vapor is almost the same density in the air, are called Rayleigh-Taylor or Kelvin-Helmholtz. And they are supposed to be unstable. And there is a recent theorem. The theorem, I think, is the most refined version, is due to C.G. Wu. And this is a theorem which contributes to the understanding of how bad is the boundary. Well, and I will tell you, I don't prove the theorem, but you see it's a free boundary problem. Now, for free boundary, there is a standard game to prove that if you have some regularity, say epsilon of the free boundary, then you can improve the regularity. It will be C epsilon plus 1, C epsilon plus 2. At the end of the day, it will be analytic. Okay? So that's a game which has been initiated, I think, by Caffarelli, Friedman, many people. It's a very classical way of looking at the thing. So the very important thing is the epsilon. Because if that says that since I know that there are solutions like that, their boundary has to be less regular than C epsilon. Otherwise, by contradiction, it will be a very nice surface. And it's exactly what CGU has proven for Kelvin-Helmholtz, saying that basically any boundary that will be curved arc, that will be a spiral that won't be too bad, will be regularized, and in fact will be regular, and will never be as bad. So in some sense, it's a theorem, it's a charm theorem of harmonic analysis, but it contributes well to the understanding of this problem. Okay, now, how much time I have? 10 minutes. Okay, in 10 minutes, I don't want to go in detail, but you see it's not very complete, what I have told you. I have told you that you have friction which behaves well, there will be no problem. If, and the other case, I am either in the generation of turbulence or in the no dissipation of energy. So the only thing I try to justify this picture is just to go from the Boltzmann equation and tell you that if I start from the Boltzmann equation, the situation is the same. So I don't want to go much in detail, but that's what I want to do to finish, okay? So, and for people which are not familiar for the Boltzmann, it will take some time, but I don't want to go in all the details. So here I have particle, and here I have the Newtonian mechanic. The Boltzmann equation is something which, for perfect gases, sits between macroscopic description and description at the level of microscopic equation. Okay? Now, the way to do that is, so that's Boltzmann, the way, and that's the Boltzmann equation. The way to do that is to introduce a function f epsilon, which is a function of x v t. This is a function which describes the density of particles. So you replace individual particle by density of particle. So it's a function which describes the density of particle which at time t, at the point x, do have the velocity v. Okay? Now, so you do that, and you can prove that in some convenient circumstances, it can be derived from the interaction from the binary interaction of particles. Now, this is what I would call the mesoscopic quantity. Now, to go back to the fluid, you write rho of x and t. This is rho epsilon. This is just f epsilon of x v t dv. You'd write rho epsilon u epsilon is the integral of the moment f epsilon of x v t dv. You write the internal energy, rho epsilon e epsilon, that you will call u epsilon square over 2 plus 3/2, maybe the Boltzmann constant e epsilon. That's a definition of the temperature that multiply rho epsilon. That will be f epsilon of x v t v square over 2 dv. Of course, you don't have equation. Now, if you write the Boltzmann equation, which is up there, here it's perfect. You write it. You have a collision operator. Due to this construction, if you multiply by 1 v and v square, this quantity will be equal to 0. So you have the conservation of the moment, and therefore you obtain that you have the first moment in terms of the second, but then the thing becomes worse, because if you want to go to higher moment, this quantity will not be closed. Now, what I started my talk just by saying that there were parameters. There were the Mach number, the Knudsen number, and the Reynolds number. Now it turns out that the basic equilibrium for the Boltzmann equation is the Maxwellian. And if you look at small, you can look at initial data which are small perturbation of the Maxwellian. And you can play with this parameter epsilon here, and how much is the perturbation of the Maxwellian. At the mesoscopic level, it is exactly what I describe as the macroscopic number like Knudsen, Reynolds, or Mach number. So if you adapt this number, you can prove, under reasonable hypothesis, that this moment will converge either to the solution of the Navier-Stokes or to the solution of the Euler, compressible or incompressible. You turn the crank, it's exactly at the microscopic, mesoscopic situation, it's the same scaling as the scaling at the macroscopic. Now, the other thing you have is that you have a nice way to represent the boundary condition. The boundary condition, rather say that in a picture, you have your wing, you have a molecule which comes in, either it is reflected, symmetric, or it may be diffused by the structure, the atomic structure of the wall in a way which depends on the temperature. There is a standard way to write that in terms of a coefficient, which I call alpha of epsilon, which is called the accommodation of coefficient. Now, this alpha of epsilon, bigger is the alpha of epsilon, more slippery is the boundary. And there is no wonder that in a certain scaling, when alpha epsilon is 1 and the reflection is 0, at the limit it will be the limit will be the solution of the solution of the Navier-Stokes if you just put q equal 1. Now, to get to the Euler, you have to enforce the Reynolds number, consider epsilon at the power 1 plus q. Now, you turn the crank, you obtain a certain number of relation, and you end up to the fact that alpha epsilon over epsilon at the limit will play the role of the coefficient, the friction coefficient, and that you will get the Dirichlet boundary condition if alpha epsilon over epsilon is infinite. It's a long story. I wrote more or less the people who just discussed that. But then I want to finish on that. You have, for Navier-Stokes, the dissipation of energy, which I wrote as in my first slide. What plays the role of the energy at the level of Boltzmann is what is called the entropy. And if I am near a Maxwellian, the entropy will resemble to the energy. The reason is in one word. It's just if I look at the function log of 1 plus z, and I multiply by 1 plus z minus z, this is equivalent to z squared over 2 when z is small. It's a convex function, which is like z squared over 2 when z is small. That's the reason why estimate at the level of the entropy for Boltzmann will produce the same type of estimate at the limit than the one I have described for Navier-Stokes, between Navier-Stokes and Euler. And that's the reason why you have the same type of theorem, which is basically that if alpha epsilon over epsilon goes to 0, then there will be no turbulence at the limit, and the limit will be solution of the Euler. If this quantity is bounded, and if the dissipation of friction on the boundary, which is described also by convex function, goes to 0, then you always go to Euler. And then if you replace the energy the dissipation of energy by something which is called the entropy dissipation, you find out that if the entropy of dissipation goes, the dissipation of entropy goes to 0 in a region that will be of the size of the Knudsen number, then the limit will also be solution of Euler, which means really that enforce the fact that the boundary condition, that to make plane fly, you need that the limit of Navier-Stokes should not be the equation of Euler, otherwise it doesn't fly. And that the boundary condition we describe that are either the Dirichlet boundary condition or the boundary condition with enough friction. That's the second thing which goes with that. And this is natural because this is what says the mathematics, and it is also natural because it's consistent with what you describe coming from the microscopic phenomena. Once again, to conclude, that the only case I know where there is a clear relation between dissipation or non-dissipation of energy and appearance of turbulence. Okay. You take the micro.
Okay. Could you describe the B term, the collision term? That
the collision term. Okay. I can. Okay. I can describe it. It's maybe I will not write formula, but I will tell you what you want. There are two way of describing it, and I will describe it. So it's an operator B of F epsilon, which is an operator which acts on the variable V, just on the variable V. For x, F epsilon is a function, or F is a function of x vt, but this, you fix these two variables, so let's say it's a B of F. Okay? Now, this operator has the...
B is describing how particles interact when they...
So B is described, that will be the next thing I want to say, but it's, or let's say it first. There are two ways to describe it. First thing, that what are the axioms of mechanics, and then I will tell you that there is only one guy like that. And then there is another way to describe it, is to say, okay, it's related to binary collision, which means I consider just that the only thing that will happen is that two particles collide. They collide in an elastic way. Their construction also for the inelastic. And then they go away with conservation of mass, momentum, and energy. Then that's at the level of Newton. Okay? Then from that, you will derive this one. And since you ask me that, there is one thing important to say, is that here you have something which is reversible, because you all know that the mechanics of Newton is Hamiltonian. Everything is it's reversible, but the equation of Boltzmann is not reversible. So somewhere appears the irreversibility. And if you are a mathematician, you try to see where appears the irreversibility. The irreversibility appears in the only proof which I know to that, which is due to Oscar Lanford. I never know. What? Yeah, Berkeley. Well, and I'll tell you what is difficult in his proof. He does the derivation, making it has a sigma is the size of the particle, n is the number of particles. We consider a situation where n c square will go to a finite number, which is epsilon, which will be 1 over epsilon, which is called the mean free path. Okay, the epsilon which was in my slide. And you want to go in this limit from here to there. Sigma is the dimension of the radius of the ball, n is their number, like the Avogadro number. Then there is a sharp, very sharp observation. It constructs that by looking only at scenario where you will go from here to there in this dynamic with a finite number of collisions. You go from here to there among the molecules with a finite number of collisions, and this collision will be just binary. Okay, that's an hypothesis. Then he proved that on this space of n particles, he put a measure, and he proved that when n goes to infinity, this set of scenario or initial data that will produce this scenario is of measure 1. That's the most difficult part. The only difficult, the rest now is classical analysis. It's the difficult part of his proof. But that said that if you go from here to there by a scenario which implies just binary collision, the same thing in the inverse may not be true. This way you have introduced an arrow of the time. You have also introduced a notion of probability, because the result will be valid only for configuration which are very factorized here and which leads to this situation. Okay? So that's the proof. Now, if you want just to do abstract mathematics, you say, I want that one to be v, to be v squared, where integrate over v equals 0. I want that the Boltzmann theorem with the entropy will be true, that if I integrate like that, this quantity will be negative, and I want that the only zero of this quantity, f, will be Maxwellian. Think of the form rho exponential v minus u squared over 2 theta, and it's 1 over 2 p theta at the power 3 half. That's the only station set. Put that in the axioms, and basically with a slight generalization, you find out that the only operator that will satisfy that will be like the one derived by Boltzmann, by Lanford, and found by Boltzmann. So that's the way of illustrating, handwritten way of illustrating that. And yeah?
You were still talking when I raised my hand. Did you finish?
What?
Okay. Is there a reference for like a nice book?
Oh, what I think will be the best. I make a commercial for a former student. Golds. Golds wrote a very nice review in some article. François Golds, he was a former student. François Golds. And I have that on my slide, on my computer. I can give you that. François Golds. And there is also a review by Villani. There are several review papers on this kind of thing, which I can find a reference for you. Of course, then you can vary the thing. But if you assume enough generality on the kernel and the uniqueness of the fact that the kernel only on that type, that was a conjecture of Serciniani, and that was proved by a student we had in Paris who was working with De Villette, whose name is Salvarani. The fact that you go from here to there, you will find in all this paper. The fact that, what I said to save time, that if you assume all that, it has to be of this type, is the thesis of Salvarani, which I can find for you also. So either you do the word work or you axiomatize and you get the same result.
Any other questions?